Let us now complete our inquiry into the early universe with even a little more speculative things. First, something about general particle physics lore. The strengths of different interactions change with energy. And one of the basic paradigms is that at sufficiently high energies, different interactions become one. For example, the electromagnetic interaction and the nuclear weak force become unified at energies corresponding to temperatures about 10 to the 16 degrees. And that has been actually experimentally proven. Similarly, it is believed that electroweak interaction and a strong nuclear force will become unified at energies of the order of 10 to the 28 degrees Kelvin, which corresponds to about 10 to the minus 35 seconds after the Big Bang. And then, to extend this, and this is purely speculative, those interactions become unified with gravity at the Planck time, 10 to the minus 43 seconds. Now, moving forward in time, the grand unified interaction splits, and that corresponds to phase transitions in the early universe, one of which could be driving the inflation. So, at the temperatures of 10 to the 28 degrees, there is electroweak interaction and a strong nuclear force. At temperatures less than about 10 to the 15 degrees, electromagnetic and weak interactions split. This is the part that's been actually probed by accelerators. Deeper in the past, we believed that electroweak interaction, strong nuclear force are joined in what's called the grand unified theories, which are actually not entirely complete, but they're reasonably strong theoretical background, and there are good reasons to believe that that's what actually happens. This is many orders of magnitude higher energies than what we can probe in terrestrial particle accelerators. So in some sense, the early universe is our only means of actually testing these theories by seeing what they predict. It is possible, but by no means certain, that it was this particular phase transition that splits the strong force from electroweak interaction that's responsible for driving the inflation. Now let's look at another important fact in the universe, and that is that there is a lot more matter than there is antimatter. Early on, people thought that there could be a symmetry, but there was simply no trace of substantial amounts of antimatter in the universe. We would have seen much more in terms of annihilation radiation and so on. Also, people who look for cosmic rays look hard to see what is the balance between particles and antiparticles, and all of the antiparticles that have been seen so far can be easily explained through normal interactions. So the universe is predominantly made out of matter, with antimatter being a negligible fraction thereof. How did that come about? This leads us into the topic of cosmic baryogenesis. Where did protons and neutrons come from as opposed to the equal numbers of antiprotons and antineutrons? The theoretical ground for this was actually laid by great Soviet physicist Andrei Sakharov as early in 1967. He came up with three conditions that need to be satisfied for this to work. First, baryon number, which we think is conserved, must be violated. And we do not have any experimental evidence for this, but it's not impossible. It has been predicted by a number of more modern theories, it just hasn't been observed yet. Second, there has to be charge and charge parity violation. For those of you familiar with basic concepts in particle physics, you know what that means, that reversals of charge or reversals of charge and parity of spins can make error of time go either way. This has actually been experimentally demonstrated as early as the 1960s. And finally, there has to be some departure from thermal equilibrium. And the expansion of the universe provides a natural way to do this. Since the universe expands, the time is not homogeneous. There is a difference between one direction time and the other, and that's what provides the necessary condition. So nowadays, most people believe that something like this was indeed responsible for establishing the asymmetry between matter and antimatter. Note, in the early universe, there could have been vast amounts of antimatter. It's just annihilated, and what's left, the small fraction that's left, is regular matter. Finally, let's talk about Planck units. This is a system of units devised by Max Planck in 1899, prior to relativity and prior to quantum theory. He asked a simple question: Meters and seconds and such are simply human conventions. Are there actually natural units that he can derive from, say, universal constants, such as Newton's gravity constant or speed of light or Planck's constant? And indeed they are. Shown here are combinations of such fundamental physical constants that yield elementary units of time or length or mass. And so for the time, it's of the order of 10 to the minus 43 seconds, and that's what's called Planck time. For space, it's about 10 to the minus 33 centimeters, that's called the Planck length. And for mass, it's about 10 to the minus 5 grams, which is called the Planck mass. Similarly, you can derive units for other physical quantities. And then there are derived units. In any case, the advantage of Planck units is that indeed they do not depend on any arbitrary conventions. They really are given by the constants of nature. But that doesn't necessarily mean that they're somehow magical. We use them as limiting units for quantum gravity, say, but we don't really know. And they may or may not be entirely relevant. Nevertheless, they're a useful set of units to consider when thinking about very early universe. So as we approach the Planck era, our knowledge breaks down. We do not yet have a working quantum theory of gravity. Not for the lack of trying. Many smart theorists have been working on this for a long time, and today we have string theory or M theory or brains and things like that. It's fair to say that none of those have yet produced a convincing unifying theory that will unify quantum physics and gravity. Nevertheless, there are prospects that that might happen. There are also theoretical attempts to think, what does this imply beyond the Big Bang? One of the interesting theories is the so-called aperiodic cosmology, which essentially states that colliding brains, which are essentially multidimensional super-duper particles, can dissipate enough energy to create all of the mass energy in the universe. There is also the concept of the string landscape, saying that there are about 10 to the 500 power different universes, each of which could have different physical constants and different laws of nature in it. Needless to say, this is completely speculative at this point. In either case, the early universe certainly provides a high-energy physics laboratory at levels that will never be achievable on this planet. And so the unification of high-energy physics, particle physics, and cosmology is likely to get even stronger. Next, we will talk about the contents of the universe.